Hello and welcome. Here we are in lecture 11. As you can see from the title on today's slides, we're going to keep doing functional programming. And by that, we mean more of the fun collections and operations on collections, right? So remember on the last lecture, we introduced map, for each, and zip, right? And they were really cool, right? With map, we could take one element at a time and transform it, apply a function to it. With for each, we did the exact same thing, except for this time, there wasn't an output saved. It's just so the whole point of for each was to generate side effects on each of those elements, right? And then, of course, we also had zip, which combines two collections into pairs of those elements. All those things, basically, some hand waving with for each is basically a one-to-one operation, right? In other words, one element goes in, one element comes out. There are times when you have many elements coming in, and you want to reduce those down to one element. That's today's lecture, right? It's how do you have these operations on collections that combine data together? So in particular, in functional programming, those two operations are referred to as reduce and fold. We'll cover both of those today. We'll also be playing around with some notations. So I'm going to encourage you to be reading the Scala API docs, sometimes to know what to do, and to help become more familiar with that, we'll cover the Scala type signatures. Additionally, we'll cover another function called zip with index, which is helpful. And just start kind of concluding with some considerations to think about when you're writing functional programming. So today, to kind of give you a foreshadow, I'm going to show you an example of functional programming I think is a good idea and it helps. And we're also going to have some where, based on my opinion, perhaps it was overdone, and maybe you might share that opinion or maybe not. We can have that debate. Let's go through it. Let's go ahead and fire up a notebook first. Good to go. Okay, like I said, so our goal for today is we want to have situations where we have combining elements, right? And so rather than simply having a new element for input element, we actually want to combine them down to things. And that sounds really simple, but there's some interesting nuances, right? For example, how do we combine things? How is that expressed? But also, what about some of the corner cases? Like what if the things we're combining, there's only one or even zero elements inside that collection? How should it behave? Okay, so let's check these out. First is reduce, right? Pretty cool, right? You can just give it a collection, and you give reduce a binary operator. So it takes in two arguments. So we learned this last time example. Here's an example of using that tuple syntax to give you two arguments A and B. We didn't bother giving them types because it's being inferred. And we're just adding them together, right? So for example, for this top portion, if we run it, we see, yes, we have original sequence over here. We can do reduce where we add the elements together. And notice how the result's 15, right? Because it's adding them all up. So it's taking two at a time and adding them all up. We also, at the end last time, with our functional literal conversation, talked about these placeholder syntax, right? That's pretty clear what's going on, right? That's maybe perhaps a more succinct way rather than writing out like this. So cool. That's reduce, right? We can kind of keep going, right? So from last time, we know we can do map. So in this case, we're going to take our sequence and square every element. It would be tempting to write something like this, although unfortunately it's not going to work, right? Because every time you use that underscore placeholder, right, it advances to the next argument. And because we want to use the original argument twice, it's not going to do the right thing. That's why I have to actually bother naming it I, because I want to use it twice, but okay. So we square all the elements, sure. And we can add them all up, right? So we can simply say, hey, sum of squares is squares reduced with the plus operator. Or we can even do it all in one line. You can see how in functional programming, with these collectives and these operations, we can be surprisingly powerful in this succinct what we're doing, right? So this one line takes this collection of numbers, squares them, and then adds them all up together. So it's a sum of squares. So yeah, here we did it kind of more verbose. Perhaps this is a better way of doing it. We kind of do it piece by piece. These are squares, and now I'm summing the squares. But yeah, with functional programming, you can do two operators in the same line. You can do it extremely succinctly. Questions, comments? Yes, or I saw a question now. So reduce returns one thing, right? So see if the sum of squares is assigned to 55, that's the result of reduce. So the functionality reduces, given a collection, it applies a binary operator until there's only one element left, and that's what it returns. And so if there's only one element left from the beginning, It doesn't even bother running the operator, it just returns it because, hey, that's what you do. For example, so seek didn't have all this and it was just seek of 0, it's okay. However, if seek was empty, how to deal with that is not to do. We're going to cover that in a minute, how to handle empty cases. But yeah, that's kind of that point. Other questions, concerns? Cool. Okay, so this is reduced, right? So already we're getting an example of times when, we have multiple things and want to somehow combine them down. Reduce seems pretty straightforward, right? Binary operator, add two things together. Or in this case, we're using reduce with a plus, but it could easily be, anything we wanted, right? We could take the product of all these things, right? Oh, because zero's in there, it makes a mess of all that, right? But yeah, it could be a gigantic number, sure. Um, okay, so now let's use reduce, right? So this code we had in Wednesday's lecture, where last week we introduced our arbiter. This is not our first draft, it's the second or third draft, right? It's not always easy to write code the first time and just get it working and then don't be afraid to revise. So when we had this last week, we were using for loops, and this was, I wouldn't say super obvious code. You had to spend a little time staring at it, but eventually the structure kind of emerges when you stare at it. And then on Wednesday, we improved this by, replacing those for loops with maps, right? The aggregation of all of the valids into a wire vec, was done by both declaring the wire vec and then inside this for loop, we were able to just, do that all at once with a map. That was really easy. Maps are really great at grabbing things out of bundles. It's a really easy thing to use them for. Uh, and then we had a few other scenarios. For example, we wanted to grab all the bits. Uh, Over here, we actually didn't even bother naming that. We just did it inline right here, right? And then this operation, connecting things deliberately, that got, of course, mapped to a for each, right? Um, which is down here. So yeah, so with the functional operators, removed all the for loops was pretty succinct. There was still this one little bit of oddness right here at the or reduction. And so if you hear that word reduction, oh wait, we just covered reduce, right? Can we use reduce? Yes, we can. So instead of using the or reduction, using the reduction from the language is a perfectly fine thing to do. But just to show we can use reduce, we did that, right? So we can instead simply reduce all those things down using the reduce operator, in this case using the or operator. So in this case, we're actually having Scala use its reduce execution to do this. It's actually pretty cool, right? Because remember, we're calling a function here. Anytime this function is called, it's going to apply this operator to these chisel objects. This is actually going to basically build up that unbalanced tree of chisel objects that you do to reductions. So it's going to be just fine in terms of the hardware it makes. I can't promise you it's exactly the same as the or reduction operator. I forget. I think the or reduction and chisel might actually be a balanced tree. I'm not positive on that. But yes, here's an example of reduce using that thing to make your code even more function based. Cool. Other questions, concerns? Cool. Okay, well, let's keep going. So I foreshadowed this a minute ago, right? What happens when you ask reduce to work on 0 elements? We saw a bunch of exceptions and errors, right? I didn't like that. What's interesting, the solution to this is actually more general. So sometimes when you're doing your aggregation of something down to fewer elements, so reduce, we had this constraint where the output type was the same as the input type. And the reason why is this binary operator took in 2 elements from the collection and produced something else new. But then once there was, a result, it would also use the result in that same operator. So basically the types had to be the same, of the input types and the output types had to be the same. What we're going to cover in a second, we're going to have the flexibility to have a different output type than input type, which sometimes that is going to be helpful. Okay, so the thing we're going to use for that is fold left. So why is it called left? Well, there is a fold right. But for now, we'll start with fold left. And maybe it's easiest if I go to a diagram, right? So given our input collection, we don't just need a function. We actually need a function and an initial value. It's going to apply this function to the initial value and the element from the collection. Gets an answer. That's going to get passed on to the function executed again on the result of the first function call and the element from the collection. So each time it goes through, it's going to apply the function in order. So remember last time with map, you can imagine a really ambitious optimizing compiler perhaps doing map every function in parallel. That's allowed by semantics, everything was independent. With fold, there's a sequential dependence here, right? Each of these function calls depends on the prior function call. There's no parallelism here. We have to kind of do things in order. And that's why the order matters, right? So fold left is saying going left to right. What does left and right mean in this context? Left means going with the indexing that's natural to the collection, right? So you combine, you do 0 first, you do 1, you do 2, you do 3. There are some times when you want to do down to the collection. There's a fold right. I saw a question. Yeah, so actually, I'm not sure reduce uses a tree. You often might care about the order of reduction, right? Because you may not have associative or commutative operators, right? So that may not be totally okay. So you'll see in a second that there's the ability to specify an ordering on reduce. Um, but yeah, for fold, from the get-go, we're talking about the ordering from the beginning because it really directly impacts the result. Because yeah, you're applying these things in order, and the order matters. And so, turns out 95% of the time, fold left is perfectly fine. You're good to go. You should be aware fold right exists, not only because it'll help you understand and remember what fold left does, but also there's a handful of cases you'll need fold right, including even one today. So let's go back to the. Go ahead. Yes. Is there? Now we're all thinking Silicon Valley about middle law compression. No, but no. There's basically fold left and fold right. Interestingly, I'll cover this in a few minutes. There's actually just the fold keyword by itself, um, which depending on the collection you're running it on, is either the same as fold left or actually could be different. But it's not so much outside in as much as it is just the more general semantics. We'll come back to that when I see the other things. So yeah, there are other possibilities. But yeah, so anyway, so remind me what fold left does, right? So we have this function, we're going to apply it to the collection, and we're going to apply it to each element in order. And the input to this function isn't just the element that's working on at that moment, it's the accumulation so far, right? So you have to give an initial value. So in this case, we're giving initial value of 0. And then this second argument we're giving here in a different set of parentheses is the function literal. As I said, because this function takes in two arguments, right? It takes in the accumulation so far and then the element from a collection, takes in two arguments. In this case, we're just adding them up. So we're doing fold left to do a sum in this case, which, um, is not a super exciting application. We'll do more exciting ones in a minute, but just semantically show us there. So here we did writing it out the long way. We can, use the placeholder syntax. We can do it for reduce like we just did a minute ago. And we can even, believe it or not, in Scala there's a dot sum, which does this. So Scala is the only language functions built in. There's this dot sum. Oops. Now, what's going to be fun though is let's see, for example, like we just showed a minute ago. Let's remove most of these elements. Everybody's still happy, right? Because reduce, you tell it to reduce on one element. Well, it was supposed to call the binary operator until it was down to one element. If it's already down to one element, it never calls the binary operator, but it's okay with that. But if we now go to 0, kablamo, right? There's a few things going on. Part of the problem is type inference. So okay, fine, we can help with type inference. We can give it a type. But guess what? Reduce is unhappy, right? Fold's still hanging in there, right? Because fold, you give the initial value, right? So if it's an empty collection, well, gee, the answer is clear, right? You give it the initial value back, right? Yes. Oh, great question. So yeah, when you're writing your function literal like this, um, you're gonna be wondering, okay, how do I know which one's the initial value versus the element? Uh, the order matters. And to make it more interesting, fold left has one order. Somebody got really clever and flipped the order for fold right, which has some cleverness to it, but also can be, easy to forget. And to help clarify that, later today, I'm actually going to show you how to read the type signature syntax in the Scala API docs. So that way, if you forget, like I do all the freaking time, you can go look at the API docs and remember how to do that kind of stuff. Um, but yeah, so go ahead and start repopulating this collection. We saw, if we want to do, for example, something like a max, here we did max, that I call it, jokingly the hard way, right? Here I'm doing max with an if statement. Um, and yeah, sure, we can do max going through the whole thing. Guess what? There's also a max built into the language. But ignoring the max is built into the language, there's a lot of things built into Scala, right? It's very convenient. Here we are using fold, right? So we have a collection, we're applying a function to each element, and this function doesn't just take each element, it takes an accumulation so far, and with fold left, we give it an initial value, and it kind of keeps passing that down the line. Cool. Questions? Okay, let's keep going. Oops, not like that. So we showed fold left, fold right. Like I said, left and right is assuming people have various mnemonics about remembering what left and right means. I would argue fold left means start from left, fold from left to right. But if you aren't sure, the way to think of it is just fold left goes ascending based on element indices versus fold right is descending. Sure. Okay. So then this is a question you had last time, and I forgot that it was actually in this lecture, not last lecture. So Scala has the ability to do what's called currying, and that is we can have multiple argument lists for a function. And we've already been seeing the syntax and perhaps not even know what it was. So for example, we just saw fold left had that syntax, right? You had this argument block and then another argument block, right? Which had a function literal in it. We were doing seek.fill earlier in the course, which took arguments like this, right? And if you actually try to put 4 comma 0, that's something different, right? You actually had to, it's not the same, right? You had to give it 2 blocks. So what's going on? So currying is the ability in a language to have multiple function argument blocks like this. And there's advantages to this, right? So sometimes semantically, it makes things more clear what you're doing. You can kind of say, oh yeah, I want this to be grouped with this. For example, fill perhaps, makes it more obvious. But more generally, the reason why you would do this is you're not required to apply all of them at the same time. That's the key thing. Let's say I had a function like sum. In order to do sum, I need to, give it both arguments, right? I can't give it only one of the two. But if I only wanted to give one of the two, I could do this, right? So this is you'd almost jokingly call this a function generator, right? Because now we've made this function plus x, which has 2 argument blocks. And guess what? So yeah, it still does the sum, but I can basically give an argument to one of them, leave the other unbound. So now I have this function f, which, because we said plus x was 1, it adds 1. But, like down here, we can make it basically be a function that adds 10. No problem with that. So we can add 10. And this is pretty cool, right? So you can kind of see how sometimes there are scenarios where you want to define a function and do things. For example, like I said, for these functional programming operators we've been using, things like map, it needs to take one element, right? But maybe there's a function you want to apply and map in multiple places, and you want to define the function such that you can parameterize that function, which will later in turn be used in a map which will only take one argument or something like that. Currying gives you that power, right? You basically can have something where you can take some of these early argument blocks, fill them out, and even populate them in advance, and then you have a function ready to go. So technically, this plus x function needs 2 blocks, right? Here we only gave 1 block here, so at this point, this function is still a function that needs 1 more argument, which is perfect for map. In this case, you have to use this underscore. It's a weird oddity to language. I don't like this. If you don't include it, what happens is it says, you know what? We can't tell quite what you want to do. If what the goal is to produce a single argument function, then you got to kind of tell it, leave the other thing unbound. But that's a small detail. This syntax, you don't need to worry too much about because you're probably not going to do it that often that way. If you do write functions like this, when you later on use them in things like map, you're probably going to be like this, in which case it's totally fine. Yes, questions? Oh, can I leave the first unbound and do the second? Great question. I don't think so. Let's find out. Yeah, I think it has to be left or right. Good question. Yes. Oh, if we just say like f like this, that should be a function that takes 1 argument. Yes, right? It's the int to int. So we can kind of even write this out, right? If I write plus x, oh, maybe I can do it like that. Yeah. So plus x, you see this syntax, it's like, wait, it's a function that takes a function. One way to think of currying is kind of just like that, right? It's like function composition, right? It's like, you apply one set of arguments and another set of arguments. So it's rather than being one function call, it's like two function calls in a way if you want to kind of, stretch your mind and tradition of that notion. Um, but like I said, usually we've been binding it. So like in this case, f where it's been bound, yeah, it's now a int to an int. And if you just grab f, yeah, it's an int to an int. This is kind of this loose end we had dangling about. We had the syntax never really talked about, but we see multiple sets of parens on the same function call. This is what enables that. It's called currying. And occasionally you'll want to do this, right? Occasionally you'll want to have a parameterized function you're going to call in map or something. And so you'll, have the part that you parameterize first, and then, the one element argument is going to be using the map call or something, or fold call like today or something. It'll be there. Cool. And continuing our detour, now coming back to the type signatures, right? So we've seen the notation used in Scala, where we have input types, output types for a function. Usually, you don't always have to, but you can put the argument input types in parentheses, and then use an arrow to convey, input types versus output types. So this is saying, hey, I want a function that takes an input of type A and produces an output of type B, right? So notice how this is kind of removed from its context, but the result of map is a sequence of type B. The original sequence was of type A, right? So potentially this function is changing. A and B can be different, they can be the same. And she's changing types. Or like fold left, for example, this is a question I was asked just a minute ago. How do I know the right order? This is reminding you, right, that the initial value is Z, or Z perhaps for zero, kind of is presumed in some cases. That's of type B. The result of the function is type B, so the thing that's accumulated and kind of passed down the line is type B. And then the original collection, which is type A, not really shown in a screenshot, is the thing from the element, right? And so yeah, so now that we kind of have some familiarity with this, we go ahead and start perusing. Open this up. Here's the Scala standard library API docs, right? Now when we start looking at some of these functions, it makes more sense. As I said before, things like map are just functions on the collections, right? So we scroll down, and there we have map, right? That was the code we were just looking at a second ago, right? You can see, yes, it takes in A, produces B. So this map, not shown, but if you scroll up to the top of this, you'll see this is defined to be of type A for this, documentation page. So these type signatures in the doc sometimes are very helpful, right, for understanding things. And so if we go, for example, to fold left, like we were just talking about, you'll see, oh, wait, there's fold, fold left, fold right. So for now, we're talking only about fold left, right? And so fold left produces, something of, produces an element of type B. This whole thing is parameterized in type B. And so yeah, it takes an initial element of type B. And so this is already one of the benefits of fold left over reduce is that, yes, fold gives you the flexibility of having different types. If we scroll down to reduce, here we have this notion. Okay, this is a more complicated type notation than I want to talk about, but this is a long way of saying that B is a subtype of A. There's a lot of very elegant stuff about how types and their relationships can be described in Scala, and I would say it's one of the more sophisticated features in the language, and fortunately I managed to get really far without fully understanding it, so you can too. Cool. Other questions? Kind of following up on the rest of this, stuff here with regards to the type signatures, right? Square brackets you're using in the beginning if it's a generic, generic meaning takes in the parameterized type for that function. But in general, like I said, the thing is the syntax is input arguments by type and then output return type. So yeah, so now you have to go to docs, you can help yourself out. Yes, question. Yes. So Seek's is generic, right? So let's go back a few slides. You saw me give it that hint, right? So before I had this, right? It said, oh yeah, this is a Seek event, right? It deduced that because of the one, right? Without the one, it actually doesn't know what type to give it. So that nothing's kind of like, base type. But I can, Seek is a generic class, right? So I can give it, I can say I want, this is going to be a Seek of strings. And sure, it can be a Seek of strings. And so The reason why we aren't constantly doing this is there's type inference. So it inferred based on the fact that there's 1, 2, 3, 4, 5 in here, it should be an int. Now, if I told it this should be a string, I think it's going to cast them. Oops, well, I got to make the right brackets first. Nope, it just says it doesn't match, right? It says, hey, you said you want to speak of strings. These are ints. They're not the same. Uh, what? It might. It might not. Okay, it did. So some conversions are easy. Now, here's the fun thing. We've covered this today, right? Or as of Wednesday. So we have a seek of ints. Let's say for some reason you can't change this code, but you really wish they were strings. Well, then guess what? We know how to do that, right? I think this should work. Yeah. Boom. Functional programming should win. So it's fun. We can do that, right? This is using that function literal syntax with the placeholder. Awesome. And yeah, ideally you change the other code so it's not such a convoluted path, but you can see how this is convenient. So things like casting collections, really anything to do with a map, right? Cool. Okay, we did currying, we did type signatures. So there's a lot of theoretical PL kind of meat today, but we're working through it. So as I mentioned a few minutes ago, right, there's actually, reduce, reduce left, reduce right, fold left, fold right. So what do these things mean? So left versus right, that is, either ascending or descending based on element order. And then people ask, well, okay, what is the one without the order labeled? Well, if you have an ordered collection, like a seek, it goes left, right? So it's reduce left, it's fold left. Now you may say, well, why is there one that doesn't bother specifying a direction? Um, Sometimes it's a way for you to program or convey that you don't really care about a direction. Hey, just add things together, reduce it. Other times you have collections, like I said, that's a more general concept. The collection itself is a collection of elements, but there's no natural order to it, right? There's no assigned order. Like a seek is short for sequence, right? Which means you're saying, hey, each element in this collection has exactly one index, right? These indexes are all unique. You may have collections that have a bunch of things put together, but there's not necessarily a index associated with things or anything, right? So in those cases, something like fold left would be hard to think about because what does that even mean? There's not an order to be following, right? So that's why reduce and fold exist. Um, what should you use in your programming? Uh, Fold left is, I guess, the most versatile one that works much of the time, right? Because we showed you how basically fold left can do things reduce can and more. Um, so that's the most powerful thing. However, reduce is simple, right? You don't have to worry about that initial value. You can just, chuck reduce at it and be done. Sometimes fold left, you start talking about thinking, oh my gosh, wait, which order is the arguments and, the initial value. So uh, if it's simple enough to use reduce, I would use reduce. And I tend to just say reduce rather than reduce left because why not, right? It's not super important about the order. Oftentimes, they're just trying to get it done. But usually with fold left, you're trying to do it in deliberate order. So I recommend saying fold left. Um, Perhaps there are some times in your code you really want to do fold right or reduce right. That's totally okay. If for whatever reason you are really resistant to the idea of using fold right or fold reduce right, you also, of course, can reverse a collection, which is dot reverse before you do fold left, which is the same thing. Um, for like long-term Scala programming, that's probably considered, clumsy or slow because you're doing extra work. Uh, I would argue, oftentimes in chisel designs, you don't have that big of collections, right? So the fact you do reverse before fold left, that's not a disaster. If you want to do reverse then fold left, I would not say that's a huge sin. Okay, let's try to use it more, right? So these are all things we saw in the first weeks of the course, and here we are redoing them with functional programming. So earlier on, we were showing, oh yeah, we could take in, a vector of, n things and add them up. So our first version, had a few different ways of doing it. Here's one way with a var. And with our var, we're able to, just use a for loop and kind of keep adding things up. And we've seen this, it works. Here's our, adders. Guess what? Instead of doing, these 4 lines, we could just say, hey, reduce, right? That's simple enough. You may not even bother putting this in its own module, right? You probably would just put this wherever you need this, right? So you can see how with the power of functional programming, we can get a lot done at a time, right? We don't have to kind of keep reinventing the wheel, thinking about things, we can express, kind of the full parallelism and get the thing all kind of described all at once. So that's pretty cool. Now, as we covered, right, that there's this requirement that we need to have at least n be greater than 0, because if we don't have this and we ask for 1, it's going to work. But if we ask for 0, kablamo, right, because we don't like doing reduce on 0 elements. Now, to the for loop's credit, the approach with var, remember we covered this a couple weeks ago, this actually does work with 0. Oh, I broke it. Ooh. Okay, wait. Oh, it's empty vector, right? How do you reduce 0 things? Yeah, that makes sense. Okay. You can't reduce 0 things. So, no, it really needs to be greater than 1, right? Otherwise, you have like 0 ports, right? So, it doesn't make sense. So it's good to be flexible, but you also got to be reasonable at some point. You can't just do anything. Yeah, so they're both are going to produce basically the same code. It's only just a difference in naming based on how Chisel internally decided to name these things. Cool. Questions, comments? Okay. So then, another example from earlier lectures, right? We built this, delay pipeline, or a shifter, if you want to think of it, right? Where we had it. Here's the functional one where you use, a recursive function. Sure. So we, kept passing down the line. This works. We want to delay 3 cycles, so we have 3 flops. It also supports when we want 0, and it just passes it straight through. This is a pretty cool generator, right? And it was pretty robust. We built this. That was neat. Now we can do that with 1 line, right? We're going to do that with a fold left. The initial thing is going to be the input. And now our function we're going to keep applying is take the last connection and the element, and then attach a register, right? So basically what's going to happen is we're going to take the last connection as the input to the register. The output register now becomes the result of this function, which doesn't get passed in last con to the next invocation. Now, if you're watching closely, you're saying, wait a second. This doesn't really seem to need a collection, right? And the answer is not quite, right? We're not using the collection for its values, we're using the collection for its length. In this case, we're making a collection on the fly just to be arranged to run the right number of times. And because this thing is going to operate on a element, the element needs to be passed as an argument, even though we aren't even using it. So yeah, you can imagine, remember before we covered how map and for each exists? We would love like a for each philosophy equivalent for fold left. Doesn't exist. But it's okay. We have this extra argument, we're ignoring it, we're dropping it. Language is garbage collected, it's okay. And yeah, same result. In this case, it is the same name. It does 0 just fine. It'll pass it straight through. Cool. And so, yeah, I mean, if I'm being completely honest with you, both expressions to me are a little bit, takes some amount of thought to read them. If I'm just granting a code, quickly scrolling through a code base, I'm like, but we're showing a way to use fold left, in this case, to do like a very controlled iteration space. So it's an example of that. The recursive function, understandable, takes a few seconds to parse and mentally kind of understand it. The for loop with var, I think might be the simplest, easiest to read. However, we're trying things out. And as part of the fun of this course is we're going to keep trying things out and code it up, see how correct it is, and see, after looking at all the options, which one we think is the most robust and perhaps easiest for others to read later on. Cool. Questions? Yeah. Oh, like what is the execution overhead you're asking, right? So that's a good question, and I only can answer this question part way. So the first order, does it matter, right? And the reason why, even though you know me, I'm a HPC guy, right? But we're already living in a Scala world, right? So it's not the same as high performance computing. But also, it's like typically a hard design, when a hard design is really big, at a given moment, you're probably not working on a gigantic collection. It might only be a handful of modules, right? Those modules you're working on may be really big internally, but the collection itself may not be that big, right? And so to first order, I'm serious when I say it doesn't matter. Like, write code that's correct and easy to understand, and you'll be fine. However, from an actual performance point of view, let's say you're like really a Scala performance freak and I really care about performance, understand a few things, right? if code is run for a long enough amount of time, not so much Scala, but the actual Java JVM JIT you're running on will optimize your code, right? And it can do a pretty good job. So the JIT's pretty cool. Additionally, the Scala compiler is no slouch. And a lot of these functional programming constructs, because of the semantics they provide, the compiler is able to do things. For example, like if you call map on a massive collection and you turn on parallel collections, that's multi-threaded for free. You didn't tell it was parallel; it just did it parallel for you, right? And so for fold is there's a sequential dependence there. So to be quite honest, I'm not sure the exact overheads in Scala versus other languages. For example, I used to do some profiling in Python many years ago, and in Python, if you use things like map, so let's say you're trying to do some operations. You have a choice between using map with lambdas, map with a function call, or for comprehension, or just a for loop. Um, and in Python, when you run like a billion elements, actually really push it, you can see a difference. In Scala, for people who really, really push it, yes, sometimes they find the functional programming operations, if you aren't using them enough to get the parallelism, might be a touch slower. Technically, a var of a while loop is often the fastest, but like that's the least exciting code. That's that's like the least correct code you want to be writing, right? Because like var of while loops, like that's going to be the least language guarantees for correctness and hardest to read. And so if you like, so clicking around a web page, from there you can find the Databricks Scala style guide. So Databricks, of course, is a large Scala user. You will see in there that they basically say, do not try to optimize your Scala code beyond, big O complexity level of optimizations. But if you do want to micro-optimize, yeah, they mentioned this. They mentioned, you can do while with var is often the fastest for an iteration. But they repeatedly tell you, make sure you profile this, make sure you're absolutely certain this is the problem, and then benchmark it after the change, make sure the change is a significant difference, and then get approval from their management hierarchy to make sure you can include it in your code. Because you can tell they don't want you doing this, right? But they acknowledge the need sometimes. So yeah, like I said, today, instantaneous, right? Cool. Okay, so that was reduce and fold. One more operator for today, zip with index. And if you've done a lot of Python work, maybe you've seen enumerate just like that. So in other words, we have a collection, and sometimes we want to iterate through the collection with the index, right? So maybe to kind of get this point across, right? Imagine doing this with for loops, right? You could say, oh yeah, for I in L, that's perfectly valid. Scala, actually, I believe you use the arrow, right? Um, you could do something like, print line I, right? This should work. Fingers crossed. Um, did I get my arrows backwards? I might have got my arrows backwards. Sorry, what? Yeah, okay. Let's try it. Okay, yeah, I said it backwards. Okay, good. You see how often I write for loops in Scala. Um, cool, so this is fine, right? Let's say for some reason you want to use the index, right? Or maybe it's better to use x, right? And so guess what? Well, then what do? Well, if you didn't know the language, you were like, shucks, I got to do 4x and 0 until L dot size, and then I can get uh, and then I'll ask for L of I, and I'll make this one I, right? If you want to actually get the oh sorry, maybe you want both, right? You want both, right? And so that's kind of annoying, right? And so what is zip with index? It's just that, right? It takes the indices and zips them with the collection, right? So we know zip from last time, right? Zip will give you a pair. And so now if you need the indices, you have it handy. Uh, you actually use this more often than you might think, because there's scenarios where you write this as a for loop code, you're probably gonna do something like this. Um, if you want to use an iterator more naturally, you try to avoid doing the indexing. However, sometimes the indexing is helpful for other things. And so thus, if you want to reconstruct the index or basically hang on to the index, You can do zip with index. And so, yeah, we did it here, sure. Here's us doing it manually. Here's it doing it actually with zip index, exact same thing. Now, given these pairs, of course, we take the products or something or multiply them together, sure. These are all fine. In this case, we took in a tuple, and using the tuple syntax, tuples start from indexing from one. I always find that so confusing. Maybe you find it easier to use the case pattern matching. So in this case, you can turn a tuple into two variables. That also works just fine. Cool. Other questions? Yeah, so this is pretty cool. Let's go ahead and start applying these to a design. Right? Okay, here's a diagram, sure. It's a zip diagram from before, just now we have the second collection is hardwired to be that range, right? So it's the indices coming in, and we pair them together. Cool. Let's do some bigger stuff. So first, let's try our priority encoder. So remember, one of the ways we did it is we did it with muxes and cascading together. So here's a net recursive function building muxes and wiring it all up. We can look at the Verilog, but remember here in the priority encoder, we're trying to find the lowest bit that's set. So you can see, for example, okay, it's only one bit set, sure, but here's 2 bits set. We want the lower of the two. Even when the higher bits are set, we're returning the lowest bit that's set because the precedence encouraged by our mux hierarchy. Okay, so this is with the recursive function. Now let's try that with a fold left, right? So a fold left, we're going to want to go through it. Now, the way we're doing our must instruction, we actually care a lot about the index in order to do these literals, right? So thus, we're using a zip with index in this case. And now that we have the index, we say, oh yeah, the thing we have so far, basically last con. And then because we did the zip, here's that portion. So this finally, here's the bit and the index. And so yeah, it all kind of merges together, right? Now, there's some complexity as well because in order to get the right behavior for this particular problem, I had to reverse it. And so it's commented on the line now. I can uncomment in a second, and that's going to be doing it with fold right. But before I do that, I can go ahead and run it as is, same answer. Yeah, so there's quite a bit going on here. I see, for example, it's called pattern matching here. We have this case statement describing the situation, right? The situation is this function takes 2 arguments. That's the syntax of fold left, right? The thing so far and the element. Thing so far, the element. The element in this case happens to be a tuple because the collection we're operating on we called zip with index, right? So basically, what do we have? Well, we had a uint coming in. And you know what? A uint's a single thing, right? And we turn that single thing into a collection of bools. That's what this conversion is here. Well, sometimes it's helpful. You want to turn each bit is a separate thing you can kind of work with. We turned it into now a collection of tuples with the zip with index. So that's why that's the element type now. And then we reversed the order for the behavior we wanted. And then we called fold left starting from 0 and did all this. So there's definitely some complexity here, right? This is, reasonable code in a sense that's going to do the right thing, hopefully. But, if you find this not super obvious when you're reading it, don't worry. It takes me a couple seconds to think about when you're writing it and reading it. But it does do the right thing. And like I said, if the reverse bothers you, we can remove the reverse and comment that out as well. And now we can make this a fold right. So now for fold right, we're going to have to do a couple things. Okay. And activate the other body. Same thing. So technically fold right is probably the more natural case. I wouldn't really call reverse in this case. Like I said, somebody for Scala was very clever. When they did fold right, they swapped now the element is here and the so far is there. So if you forgot that, you can go look at the API docs and you see, yes, they changed the order, right? Oh, sorry, let's go find fold. Right? BA versus AB. So yeah, like I said, this is, I'm being honest, right? We're using functional programming, cool. I would say it's a bit of a complex use case here. I wouldn't say this is a complete home run, but It's tricky to find tiny examples that convey these ideas. Sometimes when you have bigger projects, it becomes more apparent what you're trying to do. But also, as you play around with it more often, always becomes more familiar. Okay, let's now do the crossbar again. So we're sort of kind of rehashing code from before and showing how with more language features we make cooler and cooler code. So starting off with our crossbar, the bundle declarations from the beginning, unchanged, right? The same as before, right? So we have a message tell it, where it's going and how big it is. It sets things up for you. And then the IO for our module for our crossbar is, an input ports and output ports. It's doing all that for us. Okay, let's move on. So here's the code from last time, which, as you can see, has these nested ports. Remember, with our crossbar, we had one arbiter per output. And then for each arbiter for each output port, we had to connect to all the input ports appropriately, right? That's why it's a nested loop of 2 for loops. So we had 2 for loops and 2 for loops. In this case, we were doing on the inputs and then the outputs in the inner loop. In this case, it's the outputs and the inputs in the inner loops. But yeah, it was a lot of loops, a lot of code. But it does do the right thing. We can even go ahead and run it, and pass the test I made in this case. But let's see what we can do with functional programming. So for example, one thing we might want to do is for each of the input ports, we did this reduction where we combined all the things together. And instead, we did this reduction kind of in multiple stages, right? Where we did, we made a wire back, we went through all the things with a for loop and connected them, and then we called OR reduction. We know how to do OR reduction, right? So why don't we just use a map to grab all the things and then simply reduce them? So that's, this is a, 5 for 1 line transition? That's pretty cool. So we're still using for loop in the outer level, but inner loop we've collapsed down into a functional call. Over here, now we're doing all these kind of connections. We recognize there's kind of a pretty regular pattern to this. So why don't we go ahead and do this with a for each, right? So we're doing a bunch of connections. The whole point of for each is when you have side effects, we're not returning anything. So yeah, we're combining, in this case, the input ports from that given arbiter we're working on with the original input ports of the entire system, zipping them together. So now we have the arbiter in and the global IO in, and we go ahead and connect them all together. So that's pretty cool. To replace the inner loop with that for each call. So in these two cases, I think functional programming was a big win, right? You can see it's definitely simpler, more clearly conveys the semantics. When you start chaining together functional operators in the same line, in this case 2, I think that's okay. I think going more than 2, be careful. Even 2 sometimes also can be too many. It's not the worst thing in the world to have a val in between. Okay, have one val, do an operation, and name it. And by naming it between the 2 lines, you can tell people what's going on, right? Even right here, for example, if we wanted to maybe perhaps be a bit more pedantic about this, I could just as well have said, val, in readies, right, equals this, right? And then in readies, reduce, right? Also fine. And maybe that's more clear, right? You can kind of name things more procedurally each step. But the result is, I think, in both of these cases, we had loops. When you have loops, that means you're working on a collection, right? You're doing some sort of thing over and over again. We've seen either with loops or with, recursive functions. Those are places you should be thinking about, can you use functional programming to kind of make your life easier, right? Cool. Questions, comments on this one? Okay, so then let's crank it, right? We said, okay, we took one level of loops, turned it into a functional program, but there was 2 levels of loops in 2 places. So let's try doing both levels of loops. So in this case, the starting point, so let's see what happens, right? So we had, from the prior slide, we had a for loop with a map in it. We can now replace that. The whole point is the side effects, so maybe a for each. So in this case, changing a for loop to a for each, not the worst. Although there's a little bit of complexity increase because, we're doing a for each and we kind of really wanted that index, so we had a zip with index. Here we're doing the index directly. So I would say it's a bit of a wash here. Or maybe even this is actually even a touch worse, maybe depending how your personal preferences for code. Um, the next one, okay, we had a for loop around a for each. We can try to now go to town, right? What if we say, you know what? We're not using for anymore. We're doing all the FP operators. Let's do that without the FP operators. So what do we end up with? You might see a way to make this cleaner, but after I stared up for quite a bit, this is what I came up with, which is all of this. So we're kind of like what's going on. We have a for each, a zip with index, a regular zip. So this does the same thing, but I mean, I don't think this is better, right? To me, this is not more clear. We want to design for readability. That's one of our key tenets of this course. So that's kind of the point of this slide, is for me to deliberately push it a little bit too far, right? To show if you go too far in some directions, some philosophies, it can perhaps be not a benefit. And so design for readability should be an important consideration for what we're doing. And so, yeah, I would argue that the original version was more readable. You might even make the case that the original 2 for loop version was even the most readable, depending on your opinion. So design for readability, right? If the 2 for loops is more clear to you and you think that's very readable, go with it. For this course, have a little fun. Try the functional program and see how it feels, right? Maybe you'll like it. Um, and But understand functional programming, it's a classic phenomenon where people get excited about it and then they overdo it. And when you write this, it actually might make sense to you. Be surprised how confusing this looks when you're writing it and you're in the zone. It actually comes out pretty easily. It's actually really fun. But then you come back to it a month later, a year later, and you're like, what have I done? Right? Or worse yet, it's really clear to you, but then your coworker working in the same code is like, what was he doing? Right? So this is why, I'm encouraging some amount of caution and restraint, but we've seen some examples where these operations, it's just too effective, right? Things like map to grab things is extremely effective with the functional programming approach. Reductions, also easy. For each, in some cases, right? Like going back a slide, a nice tidy for each like this, in this case with zip, not even a zip with index, pretty clear, right? I think that's pretty nice. You have an arbiter in to IO ends, right? Here you do a lot of parsing of, what do these indices mean? Here it's pretty clear what we're doing. So I think this actually is better, I would argue. So be judicious, but also be afraid to just try writing things and then write it the other way and look at the two and decide what you think is more readable and pick the one that is going to be more correct, easier to maintain, and more readable. Cool. Questions, comments, opinions? Is anybody going to defend this? Did they say this is better? Does anybody like this one more? Okay, nobody's defending it, so it is complicated. Um, cool. So yeah, so kind of there's a little bit of functional programming content for the next lecture, but I still want to conclude today by talking about, like I said, this is a feature, right? It's not a requirement. I may ask you to do it for a homework assignment explicitly, but other than homework assignment explicitly requiring of you, especially when you move on to your project, you'll have some choices what features you're using. You want to, do things that make a good result, right? So using functional programming correctly, you can, identify common patterns, things like grabbing a signal of a bunch of bundles, convey that really succinctly, improves readability, simplifies the code, we're all happy. You make it too crazy, you put, zip with index, map, reduce, map on the same line. It's hard to read and understand, can be brittle, you change one thing, everything breaks. With a lot of this type inference we're seeing here, if you go on and change one of the components, it's not obvious what the intermediate things are anymore because it's not all labeled. So as a counterpoint, think about, would a simple for loop or even recursion be more clear? I say 2 to 3 FP operations per line at most. 3 should be rare. I think 2 is a good limit. If you find your function literal is getting really long, that function you're using, perhaps you should just name it as a function, right? So rather than having this inline syntax like we had here, I mean, technically this is perfectly valid Scala and it works fine in this case, but you said if it starts getting really, really big, you can just define a function and make it really clear this is a function you're calling on something. Ooh, that's a new one. What did I just do? Okay. Cool. Any final questions or comments? Okay, that's all, folks.